Okay, here we go. How was the quiz? Awful. Huh? Yeah, see, that's a positive thing. What was awful about it? Yeah,
For me, the chromatography stuff is still pretty mixed up in my head.
yeah,
I haven't really sorted it all through. I know all the stuff, but like really sitting and thinking about it, I just
yeah. It is. Yeah, it is a kind of a. So for some of you, might be a first exposure or a second exposure, but the first time wasn't so great. So yeah, it is expected that it's kind of new material and can be confusing. But hopefully, when we go through HPLC and GC lectures and labs, things will sink in a little bit better.
If there's like calculations like that, they're still like short, like quick quizzes. So I just felt like super rushed.
Rushed. Well, we did take about almost 30 minutes
Oh,
since we
okay,
started.
enough.
I did say it should take 10 minutes, but I really never rush students. I let you take your time, even if I say 10 minutes. So do take your time, and if you're taking an exam and you still need more time than the exam time, know that I will take you somewhere else to finish the exam. I never rush you. You can take your time. But usually when I design a quiz or test, I try to make it an average of what an average student time would need, but there is no rule around that. Um, okay, so we will be grading the quizzes. I will develop a key and Chelsea will be grading the quiz. I will scan through them after Chelsea grades them, and then we'll turn them back within a week. And then you can look at the key online that we post. If you have questions, we can discuss. Okay, since you've studied, I guess you will probably know this now. Can you name examples of adsorption chromatography? Yes? No.
Ion exchange.
Lauren. Huh, I, delayed response. Huh?
Ion exchange, affinity, and absorption.
Ionic exchange, affinity, what did you say?
Ion exchange, affinity, and then hydrophobic.
Yes, hydrophobic interaction chromatography. They're all examples of adsorption chromatography. Okay. Um, what molecular interactions between solute and stationary phase are involved in size exclusion? Yes, Julian?
It's just physical interaction.
Yes, there shouldn't be any physical interaction. Ion exchange? Yes, Justin? Electrostatic. Hydrophobic interaction chromatography?
Hydrophobic.
Hydrophobic. And what was affinity chromatography? Yes, Keaton? Everything. Hydrogen bonding, electrostatic, van der Waals, hydrophobic. It's very specific. It could be all or a couple of those, depending on the compounds. So what's the difference between cation and anion exchange chromatography? Yes, Megan? Megan, right?
No.
You're not Megan? Gosh, am I confusing you? Oh yeah, you're none. Sorry. Okay, you guys take the quiz and I get lightheaded. All right. Okay. Go ahead now. Say that again. Yeah, so what's the charge on the functional group for cation and what's the charge on the anion on the function? So the functional group on the phase on the stationary phase is positive if it's cation exchange? Ah, so see, this is the most common mistake. Yeah, when you hear cation exchange, so you are exchanging positively charged. So what's on the column is negatively charged. Otherwise, it won't interact with the column. So that's where it gets tricky, cation versus anion exchange. The opposite is true for anion exchange. Um, how do you increase the strength of the mobile phase in reverse phase chromatography? Sarah?
increase the concentration of the organic solvent.
You increase the concentration of the organic solvent. Okay, great. How do you increase the strength of the mobile phase in hydrophobic interaction chromatography? Yeah, go ahead, Emma.
Increased concentration of solvent.
Increase or decrease?
Oh,
Decrease concentration of salt, yes. Ion exchange chromatography, yes, Monique? Exactly. You increase the salt concentration or either increase or decrease the pH depending whether it's cation or anion exchange. What about affinity chromatography? Yes, Lauren?
changing the molecules of the pH or adding more ligands that put it on the
Very good. So we change the characteristic of the mobile phase either by changing pH or ionic strength or temperature, for example, or we add ligand to the mobile phase that is similar to the ligand attached on the stationary phase. What's the order of elution in hydrophobic interaction chromatography? What comes out first? What comes out last? Yes, Lynn? Yes. What about ion exchange if you have, um, regardless if it's cation or anion, what would elute first, what would elute last? Yes, Amanda?
It's the least to the most.
Least what?
Ionic.
Least charged?
Yeah, least charged.
Yes.
Most charged.
Yeah, okay. So, yeah, the least ionic valence.
Yeah.
Yeah, okay. Will come out first. Size exclusion, Lucy? The largest will come out first because the small one will enter the pores and get more distracted in the column. All right, cool. You guys studied. Um, that's great. Moving on. All right. Claire told me nobody's going to focus today with you. Yeah, she knows. She's a student still. And I remember when I was a student, after an exam, I didn't want to do anything or a quiz. But I'll try to entertain you a little bit today and go slowly, and we'll continue next time. We have 20 minutes, so we'll see where we get with um, resolution, which is an important task you want to do when you do chromatography. You are after separating. By definition, separating meaning let them come out at different times. You don't want compounds to come out in at the same time. You defy the purpose of chromatography. So you want to develop a separation. So once you are running it, you're running a sample, so you want to know certain things about the samples. So before you actually start running the samples, so you want to know, okay, what's in my samples in terms of components? Do I have a group of ions? Do I have a group of phenolics? Do I have a group of large molecules and small molecules? What do I know about the sample and the constituents of the sample? That's the first thing you want to know. And then how many components are we resolving? So let's say in one of the labs you're going to determine or identify phytochemicals in soybeans. So there are 12 different phytochemicals of the same class. So you want to know, okay, in my sample there are 12 different isoflavones, so I need to make sure that I can see 12 different peaks in my chromatogram. What degree of resolution is needed? Do I really need the samples to be very much separated, individual peaks? Yes, you want to, if you want to quantify. If you want to get the area under the peak, you cannot do that when you have peaks coming out close together. You cannot really draw a line and say, okay, here's the area of peak 1 and here's the area of peak 2. But if you're looking at identification, if you don't have perfect separation, that's okay. You can still probably look at the spectra, which is the, what do you call it, spectra? It's when you plot absorbance over wavelength. So you can say, well, okay, I can detect the spectra for this one, and I can detect the spectra for that one. I can identify them. So sometimes you do not need that grade of resolution, and sometimes you really do. depending on what the purpose is. So sometimes you go for speed. So for speed, then you would go, okay, I'm just going to have a quick flow rate. I don't care for them to be separated really well. And sometimes, no, I need to slow down. I need to have good separation, even if that means longer analytical time. And then that answers this. Is it qualitative or quantitative? Am I after identification or quantifying compounds? Okay, so you are working a researcher, let's say you're a graduate student or even an undergraduate researcher, or you work in a company in a research lab, and somebody told you you're off to analyze carotenoids. Okay, how do you go about choosing a method? What's the very first thing that you do? It's not going to be on this slide or anywhere in the slides. What's the first thing you want to do when you're given a task? We need to determine carotenoids in a certain grain. Simple. Yes, Ryan? That's the first thing you want to do. Look what's published in that area. What have people done before you? You'll find hundreds and hundreds of articles related to determining carotenoids in different grains. So somebody has looked at it before you. Almost 99% of the time, somebody has done this before. There is a method that is established. Sometimes there is a standard method of analysis that is established. So that's the first thing you want to go do. Okay, I'm going to look for research articles or standard methods to determine what method would work best for me to determine carotenoids in my grain sample. And then based on your references, some might say, okay, you need reverse phase chromatography. Others might say, well, no, you might be able to go with not polar, hydrophilic interaction chromatography, which I didn't talk about. So, or hydrophobic interaction chromatography, no, it doesn't work. So you might actually find out that there might be several chromatographic modes of separation that would work. Then you go and then determine, what do I have in the lab? What could be more feasible? What's less costly? Do I have the particular column I need or not? And then you choose a chromatographic separation accordingly. And then choose of stationary phase. So if I say reverse phase chromatography, do I choose C18 column or C30 column? How do I determine that? Then you try to determine what's the best phase that you can start with, and what would be a mobile phase. Again, oftentimes all of this is given in a research article. You would just say, in this research article they use C830, they use methanol acetonitrile combination as a mobile phase, and that's it. You have a starting point. And then you determine, okay, do I want to go with isocratic elution or should it go with gradient elution? What would be my flow rate and what would be the temperature? Okay, isocratic elution, if you have compounds that are very different in their relative polarity. So one is very polar or relatively very polar, and one is relatively non-polar. So one will elute very fast, and one is going to take an hour and a half to come out of the column. So isocratic elution will not work. If you just keep a constant concentration of your mobile phase, one will come out and one will sit there for an hour and a half. So probably gradient elution would be better, because once the first one comes out, the first polar one comes out, you can increase the organic solvent concentration and let the second one that is non-polar come out in a decent amount of time. Flow rate, this is important when we talk about efficiency of the column, efficiency of the separation. Flow rate plays a very important role. That means, what's flow rate? Does anybody, the ones that did the lab today, What is a flow rate? What do I mean by flow rate? Several of you took the lab today. How many milliliters per minute of the mobile phase go through the column? So flow rate needs to be adjusted and optimized. If the flow rate is too fast, your compound will come out too quickly, and sometimes compounds don't have enough time to resolve from each other, to separate from each other. So you don't want that. You also don't want to wait and wait and wait. So you want to find an optimal flow rate where you reach equilibrium fast enough between stationary phase and mobile phase, and then get them out of the column in a reasonable amount of time. So this is important. Temperature is important. What happens to the viscosity of the mobile phase when the temperature goes up? Please put mobiles away. If you need to use the phone, you're welcome to leave the room. Okay, what happens, say that again, what happens to the viscosity? It decreases. So when the viscosity decreases, your mobile phase has better mobility. So it can carry your solutes more efficiently, and you can reach equilibrium faster. So you can shorten your analysis time. But again, there's always an optimal temperature you don't want to exceed, because if it goes so fast, then you will lose resolution and defy the purpose. So between flow rate and temperature, there's always an optimum you need to figure out, either from a previous paper or you do that in the lab by trial and error. You might start, the paper might say 1.2 milliliter per minute, but as researchers, we know you can never reproduce 100% what people publish, because you always have something different, some variable that's different in your equipment than what's in the paper. So you would want to tweak that a little bit. For them, it might have been 1.2, but for you, maybe it's 1.1 or 1.3. So you just have to always tweak that to get to the best resolution you're after. Here, we're illustrating that sometimes for the same sample, you have multiple options. So you can have ionic. If you have ionic samples, you can do ion exchange chromatography. You can do reverse phase with ion pairing chromatography. That I didn't talk about. Ion pairing means if you have an ionic species, you can actually mask the ion on the speech by adding counter ion. So let's say you have a negatively charged compound. You add a positive charge counter ion. It masks the charge. Then it can react with a hydrophobic media. Okay? Or if it's non-ionic, you can do a reverse phase chromatography or some other chromatography, or sometimes you can do either reverse phase or normal phase for the same compound. Again, what I'm trying to say here is not always one choice of separation that will work. There could be multiple choices that you can choose from, but again, you go with your experience, what you have in the lab, what's easier, what's cheaper, what has been more published in terms of something that would work. Okay, so some terms that you want to be familiar with. So there is something we call retention volume, and there is retention time. Retention volume is the volume needed to get the sample or the solute out of the column. Okay? The retention time is the time associated with that volume that gets that compound out of the column. Most often, it is always retention time, what people talk about. So let's say for peak 1 here, the retention time is TR1. That means retention time for peak 1 to elute. And then the second one will have a retention time R2 for the second peak to elute. So the very first thing you do, those of you that we did HPLC, the first thing we did is we looked at the retention time of a standard, of a caffeine standard, and we looked at the retention time of your caffeine in your sample. That's the first identification that you would do. It's very simple. You just look at the retention time and you go, this is most likely caffeine because it's coming out in 15 minutes, similar to what your actual standard or known compound comes out. That's the first thing that you would do. However, oftentimes two compounds come out together. If they come out together, you have to do a further separation procedure. So you want to change your separation in a way that allows them to separate, to resolve from each other. So how do we determine the separation? There is something called separation factor, this alpha here. Did I talk about solvent front? I didn't. So the solvent front is basically the time it takes for the solvent to go from time 0 to reach the detection, to reach the detector, basically. So this is what we call the solvent front, or mostly it's the void volume. And it is not containing anything. It should not contain any sample that you're actually trying to detect. So the adjusted retention time is basically used when you are using different systems. When you're using the system that gives you a retention time of 15 minutes, another system gives you a retention time of 16 minutes. Why is that? Because one system might have longer tubing than another system, so the compound took longer time to get out of the column, out of the detection. So oftentimes if you want to compare your retention time to another instrument, you adjust based on where does the solvent front comes out. So you get an adjusted retention time. So T prime R1 and T prime R2. You use that to determine the factor of separation. So T prime R2 over T prime R1, if it is equal to 1, then they're not separated. If T prime R2 equals T prime R1, they are equal, then alpha is 1. You don't have separation. You want almost always T prime R2 to be bigger than T prime R1 so that you actually get them resolved. So you want the value to be greater than 1. So resolution. The resolution of the peak is directly related to the difference in elution time or retention time, and inversely related to the width of the peak. So I don't know if you heard me say sharper peak. So when you have a sharper peak, this is what you want. You want a really sharp peak. You want something that looks sharp and nice like that. You don't want this. What does this mean versus this? So if you have the column, so you start off with your compound on the column. It will diffuse down. We'll talk about diffusion later, maybe next time. And then it's going to go in and out as well. So you have equilibrium between the mobile phase and the stationary phase. And then you have diffusion. If you have diffusion quite a bit, eventually this is going to spread out. It's going to spread out as it goes down. And then because it's spread out, this is going to look like here, like this one, because it's spread out. You don't want that to happen. You want your movement to be more this way rather than this way. So you want it to be a sharp peak. If it's a sharp peak, you have very good resolution between two. If they're large, you might have an overlap. They're diffused into each other. So you will end up with something like this, and then you'll have that. So you'll have two peaks that co-elute because they both diffused quite a bit. But when they're sharp, you'll have very nicely resolved peaks. They don't diffuse so much longitudinally, but rather they go in and out and equilibrate between your stationary phase and the mobile phase, and then they move in very tight space. So resolution is therefore inversely proportional to the width of your peaks. When it's wider, you lose resolution. When it's sharper, your resolution is better. So that's how this is read. And also, when there is enough difference, the difference in time of retention is greater, you have better resolution. So two things play a role with resolution. Resolution is a function of three things. You have the efficiency of the column, which is component A, N is number of theoretical plates, and we'll talk about that next time. B is capacity, and C is selectivity. Oh, the other way around. B is selectivity and C is capacity. Sorry. Okay, so each one of these, the efficiency, the selectivity, and the capacity, impact resolution. Efficiency is directly related to number of theoretical plates, and with this note, I'm going to stop and talk about number of theoretical plates next time.